Okay. Chapter 1, Lecture 2. Let's get kicking. Talking about atomic theory. Atomic theory. Well, let's go back to the beginning. Aristotle versus Democritus. Okay, a couple of Greek philosophers. In Aristotelian philosophy, all matter was infinitely divisible. So, according to Aristotle, matter is composed of both a substance and an essence. Okay, it was a dualist theory. Okay, the two different, entirely separate things that make up matter was for Aristotle and his followers, the substance and the essence. Okay, now for them, the substance was all the same, from one type of stuff to another type of stuff. What changed was the essence, the spirit, the soul of the thing. Okay? So a horse, when it eats grass, it takes in the substance of the grass and then transforms the essence from the essence of grass to the essence of horse. Okay? In the same way, a carpenter taking a table transforms the essence of the wood without altering the substance. Okay? So Aristotle and his philosophy here was very popular with religious types. Because of its dualist nature, matter and soul, even though it was a little bit weird for some religions. On the other hand, you have Democritus and Epicurus, okay, where matter is composed of different kinds of substances, okay, these different fundamental particles of matter. Okay. So in Greek, tomos means able to be divided, able to be cut. So atomos means unable to be divided, hence the modern word atom. So for the Epicureans, there is no soul, there is no spirit to matter. There's just different kinds of substances. Okay? And so those are the big distinctions between the Aristotelians and the Epicureans. Where Aristotelians said matter is infinitely divisible, there's no smallest particle. The Epicureans said, yeah, there is. And the Aristotelians were dualist, with matter having both a substance and an essence. The Epicureans were monist. Okay, there was only the substance. Okay? Thus, the Epicureans were very popular with atheists. Okay? In fact, they were largely identified with atheism for a very long time, and thus they were sometimes violently suppressed. But they stuck around here and there, and thus their names survive to us, as well as some of the words. Now, moving on, we have Dalton's atomic theory. This is the first of the dead white guys you'll have to know his name and something about him. In the early 19th century, he came up with atomic theory. He said that these are the postulates, by the way. A theory is made of postulates or statements. Okay, so atomic theory, according to Dalton, it's been updated since then. All matter is composed of minute, indivisible particles called atoms. Atoms come in varieties known as elements. All atoms of an element are identical. All atoms of different elements are different. Atoms can combine in whole number ratios. This is known as the law of definite proportions. Hint, hint, that's one of the things that's likely to show up on a test. So atoms can combine in whole number ratios to form new substances called compounds. Compounds have properties different from the elements that make them up. And finally, atoms can combine in different ratios to form different compounds. That's the law of multiple proportions, hint, hint. And those different compounds will, once again, have different properties. Okay. Now, like I said, we've updated atomic theory since then. Okay, he did a really good job laying all this out. This was in, I think, 1805. But it wasn't entirely correct. We now know, for example, that atoms are divisible. Atoms are divisible. We know about subatomic particles. Okay, you can break them down into smaller particles. We also know that atoms of an element aren't all perfectly identical. They come in varieties known as isotopes, where they have different numbers of neutrons. We also know that whole number ratio thing is kind of bent, for example, with alloys. A theory doesn't have to be perfect. in order to be a really good theory. Dalton's famous because he overturned Aristotle. Okay, it's hard to understand now how big a deal that was, but Aristotle was science in Europe for about 1600 years at this point. Overturning Aristotle meant that he had overturned the foundation of science, and that made him internationally famous. Okay, so literally, a Frenchman showed up. He wanted to speak with this genius of chemistry, and he was surprised to find him teaching elementary school. Dalton was a Quaker, and they were famed for their humility. All right. So, how did Dalton overturn Aristotle? We have a quote attributed to Newton. If I have seen farther, it is by standing on the shoulders of giants. So, Sir Isaac Newton, 1675. Except, actually, we can trace it back further to Bernard of Chartres, circa 1120. Actually, it goes back to a Roman named Priscian. Actually, it goes back. Okay, look, the point is that this is not a new idea. We build upon the work that comes before us. Okay? So, throughout the centuries, people, didn't just stop with Aristotle. They kept exploring, kept learning, kept trying to find new things. And centuries of labor from the coming of the printing press to Europe had transformed alchemy into chemistry. Okay, people had finally been able to write down their ideas and share them with one another. And bad ideas were discarded, good ideas were kept, and they were able to develop it. So alchemy went from being a thing practiced by mystics in isolated towers, and it turned into chemistry, a science that was practiced by lots of people who were constantly talking to one another. So Dalton looked at centuries of evidence and saw that no matter what you did, there were these sort of inviolable postulates. And the only explanation for all of it was atoms. Okay. So let's go ahead and disambiguate something. Fact versus theory. Okay. Facts are small things. Okay. They're kind of useless by themselves. Okay. It takes billions and billions of facts before you have a decent amount of information. Okay. You have to collect lots and lots of data, lots and lots of individual facts. Okay. A fact is almost useless by itself. Okay. Laws are the next step up. Laws are the relationships among the facts. Okay. So going back to Newton, Newton did lots and lots and lots of observation of things in motion in order to derive his laws of motion. Okay? The three laws, force is equal to mass times acceleration. An object in motion tends to remain in motion. For every action, there's an equal and opposite reaction, right? Those are the three laws of motion. But that took, years of work observing the way things actually move and how they respond to different forces and things like that. Okay? So you have to gather lots and lots and lots of facts. You see the relationships between those facts. Those are the laws you're looking at. Which finally leads us to the theory. The theory is the top of the pyramid. It's the best. It's the thing we're all looking for. It's the explanation that fits all those laws and facts together. Okay? So if facts are grains of sand, laws are bricks, the theory is the house. Okay? So when Newton came along with his theories of motion, with his theories of gravitation and so on, he took just the bare bones of what motion is, and he put it all together into a framework, an explanation that actually made sense. Okay, so theories are diving beneath the surface into the fundamental stuff of nature to try and find out what is really going on. Okay? In the same way, Darwin took the billions of facts, by centuries of biologists observing nature, and he distilled those down into some laws about the ways living things change generation to generation. And he realized that the explanation for that was the theory of evolution. So this is a good example of the difference between the way specialists can use language versus the way the public at large can use language. Okay? So every profession has what's called jargon, okay, a specialized vocabulary for use within that profession. And that jargon can be very, very different when it comes to the way it's used in popular culture. So, for example, back in grad school, when I was studying glass forming materials, there was a property of glass forming materials um, that described the relationship between the viscosity of a liquid and the temperature of the liquid. And we called it fragility because we were dealing with glass forming materials, but it has nothing to do with what most people think of as fragility, that being how easy something is to break. So that jargon can get very, very abstruse. It can get very obscure. Now, the word theory in scientific jargon is very, very different from the word theory in everyday use. In everyday use, theory means a guess. In science, a theory, it means not that. For science, if we wanted to talk about a guess, we have a word for that. That word is not theory. It is hypothesis. Okay. A hypothesis is a guess. Okay. We have, the two portions of the word. We have hypo, which means weak or less, and then we have thesis, which means statement. Okay. So a hypothesis is a weak statement. Okay, a guess. Okay. So a theory is not the same thing as a hypothesis. It's not just a guess. Okay. It is the very opposite of a guess. A theory is the result of years, if not centuries, of hard work by lots and lots of people. Okay. So, moving on. Here are some laws you need to know. The laws of conservation. So, to conserve means the tendency of a property to remain constant over time. There are other ways it can be used. Again, jargon. This is the meaning we're using here. So, laws of conservation refer to things that remain constant in chemistry and physics, and other places, but in chemistry and physics, we really do care about this. The laws of conservation are some of the things that make it possible for us to do work, and also it's kind of a fundamental fact of reality. A thing that is conserved will neither appear nor disappear. Okay, in other words, magic isn't real. Sorry. However much of a thing you start with, you will have at the end, if it is conserved. Okay, so mass is conserved, or matter is conserved. Physical stuff doesn't just appear or disappear. Energy is conserved. Okay, charge is conserved. So if you start with a net positive charge, you will have to end with that same net positive charge. Okay. Depending on what work you're doing, some of these laws will be more important. Conservation of matter is what will allow us to balance chemical reactions later. Conservation of energy will really help us out a lot with some work we do later on in the course. Conservation of charge, for this first semester, that will have a limited application. But it will be very important to helping us with that particular application. I'm talking about balancing redox reactions. It's a special class of reaction with a special kind of balancing. But charge is conserved. It's one of those facts of reality. Useful to know, especially if you intend to continue with physics or chemistry. Okay, so that does it with this second doohickey thingamabob, kajigger. This second lecture. I will see you again in the next lecture when we talk about something else.